Hello everyone, I'm Jiayi Tian. In this video, I will guide you through a machine learning project on liver disease classification. We'll dive into the datasets, processing technicals, model selection, performance evaluation, and real-world impact of our results. Okay, let's get started. Well, the first part is about the background and dataset of this project. The goal of the project is to develop a machine learning model capable of accurately classifying the patients as either having the liver disease or not. The dataset used for this project contains a variety of physiological indicators, age, gender, and other medical attributes. Well, the target variable is binary, with 1 representing the presence of the liver disease and 0 indicating its absence. The primary challenge in this project including the class imbalance, which can bias the model toward the majority class, and the complex featured relationships, like those indicators may interact in non-linear ways, and overfitting risk like achieving perfect accuracy during the training but requiring careful evaluation on unseen data. And by addressing these challenges, processing and featured engineering technicals are of great importance. Next part is about the data processing. Firstly, we load the dataset using the pandas read CSVs and inspect its structure, including 418 rows and 20 columns. And the next step is identify the outliers. We used two key zeros, which calculates the interquartile range. Outliers are defined as values beyond the specific range as shown formula on the screen. These outliers are handled using the visualization, which caps the extreme values to a specified percentile range. For features with missing values, we fill them with zeros to avoid the data loss. And categorical features such as sex are converted to numeric representations using the dummies encoding. And for instance, the sex is split into binary columns, including the sex M and sex F. And the drop first equals true parameter avoid the multicollinearity by removing one category like the sex F. Correlation matrix and heat map are generated to visualize the relationships between the features and identify the highly correlated features. And we use the column names from the dataset to identify the predictors and the target variable. Next, the data is split into the training and testing subsets with 80% allocate for training and 20% for testing. And then we standardize the numeric features using the standard scalar, transforming the data to have a mean of 0 and standard deviation of 1. Finally, to address the class imbalance, the SMOT is applied to generate the synthetic samples for the minority class, ensuring a balanced training dataset. Next part of the code evaluates the performance of a machine learning pipeline on the holdout test dataset. The pipeline previously fitted on the training data is used to predict the target variable for the test set, and the predicted results are then assessed using the two key metrics. The first one is accuracy, which is about 64%, indicating that about 2/3 of the prediction are correct. And the second one is the confusion matrix, which highlights the model's performance. And additionally, the pipeline previously achieved a coarse validation accuracy of about 67%, showcasing the moderate consistency across different data splits. And these results suggest the potential areas for improvement in model performance, such as refined data, processing steps. The project used PyCaret to automate the process of model selection, tuning, and evaluation. The pie-cracked pipelines begin with a setup which normalizes the features balanced class with mode and sets a target variable. The function compare models evaluates multiple models and select the best one. And the function create model generates the chosen model which can be fine-tuned with the tuned model and finalized with the function finalized model for development. And finally, the predict model and the evaluation model, the two functions, assess the performance using the key metrics like the accuracy and the confusion metrics, streamline the model selection and evaluation. Well, the next part is about model evaluation. Those metrics are mainly used in this project to evaluate our models. The accuracy measures overall correctness, and AUC-RC curve evaluates the model's ability to distinguish between classes. And recall is important for detecting the liver disease cases correctly. And precision measures how reliable positive predictions are. And F1 scores is a balance between the precision and the recall. Well, some findings can be concluded from our results. Based on the results, the Extra-Trees classifier achieved the highest overall accuracy and precision among the tested model, making it the best performance model based on the course validation metrics. And our models such as the random forest and the light gradient boosting machine perform similarly in terms of accuracy but have slightly lower precision and recall scores. Well, the worst performance model, including the dummy classify and SVM, which show limited capability to classify the effectively in this dataset. Well, for the Extra-Trees classifier, the course validates result shows constant performance across the folds, with a mean accuracy of 75% and a recall of 60%. The standard deviation are lower, indicating a stable performance across the data splits. When the Extra-Trees classifier is trained on the entire dataset and evaluated on the holdout test set, it achieves a perfect score, indicating possible overfitting, which requires some further investigations. The second picture visualizes a complex pipeline from the data processing to model training with the Extra-Tree classifier. Well, to improve it, additional steps such as hyperparameter tuning or adjusting the processing techniques can be considered. These results analyze the importance of balancing model complexity and performance to achieve reliable real-world outcomes. Well, the next part is about some applications in the real world and suggestions for further improvement. Well, the hospitals can use this model for early screening to identify the later disease patients before the symptoms worsen. And it can also integrate into the healthcare system to assist doctors in risk management. And health organizations can leverage such models for predictive analysis in public health. Well, as for the potential improvements, the feature selection techniques like the PCA or featured importance can be used to enhance performance. The deep learning models like the CNNs or LSTMs can be implemented for more complex featured extractions. And hyperparameter tuning using the grid search CV can be applied to optimize the model. Well, to summarize, we explored the liver disease classification using the machine learning, addressed the data processing changes, tested multiple models, and evaluated their performance. Well, our best model show highly accuracy. Our fitting remains a concern, and further improvements can be made through a fine-tuning and ensemble methods. Okay, that's all for my presentation. Thanks for listening.